Hello, everybody. My name is Morgan. I am an AmeriCorps member with Conservation Nebraska's Common Ground program. Tonight, we have a presentation with Dr. Dan Snow over PFAS in our domestic wells here in Nebraska. It's going to be a really good topic to go over. Just a few things that I'd like to remind everybody about. Your cameras and microphones are turned off, but if you do have some questions, please put those into our chat or Q&A section as we anticipate hopefully having some time at the end so that we can go over some of those questions with everybody. And then we will launch a poll towards the end of our webinar tonight. If you guys don't mind filling out a couple questions, it helps us plan some future events and some things that we would like to know. So further ado, I will hand it over to Dan and we will get started.
Well, thanks, Morgan. I appreciate the opportunity to talk about domestic well water quality and per and polyfluorinated fluorinated alkyl substances. Sorry, that's kind of a mouthful. It takes a while to get used to saying that. It's not a super long presentation, so I hope we have time for quite a few questions at the end. I just wanted to kind of give you an overview and show what my perspective. Oh, looks like I can't share my screen. You might have to give me permission.
All right, just a second.
You should have screen sharing permission. Let me see. Are you able to share now?
Yep.
Okay, awesome.
Let's see if that one is. Okay. You see the slides?
Yes.
Great. So I'm going to talk about a little bit about domestic wells and well water quality, and then follow up what has become a pretty hot topic lately, per and polyfluorinated alkyl substances, or PFAS. I'm a research professor and director of the Water Sciences Laboratory, part of the Nebraska Water Center and Daugherty Water for Food Global Institute. So I've been working on water quality for a long time. So this is kind of an introductory slide. I use this a lot in the classes that I teach on water quality. Basically, it shows the hydrologic cycle, which I think many of you are already familiar with, and how we interface with that hydrologic cycle through our water use and reuse cycle. Source water, drinking water. From drinking water, we go to wastewater, and that wastewater is often discharged into receiving waters, which end up back in our ecosystem and then reused. And that water gets reused over and over again, sometimes in the space of a few months, often over the space of decades, years to decades. So it's just these contaminants that I'm going to be talking about really become apparent mainly because of the connections that we have through our water use and reuse. So a little bit about drinking water quality. Basically, we define drinking water quality as chemicals and microorganisms that can affect human health. And that goes through a really rigorous, complex evaluation of risk, including potential for exposure, toxicity of the substances that we're measuring, and then finally methods for detection. And really it's that last bullet, the methods for detection, that have allowed us to start measuring and worrying about things like PFAS in our drinking water. So fortunately in the United States, which is, we're really pretty well positioned for public water systems. Those public water systems are protected under the Safe Drinking Water Act. And that act includes a lot of regulated inorganic contaminants, including nitrate and nitrite, pesticides and solvents, as well as radioactive substances and microbiological contaminants such as pathogens. And really those contaminants we make measurements and then we evaluate those concentrations to potential health effects from long-term chronic low-level exposure. And in the US in particular, most public water supplies have a very low probability of exceeding what we call a maximum contaminant level, the MCL, that I'll talk about a little bit with respect to a few contaminants, including PFAS. So a lot of you are probably familiar with this nitrate MCL and maximum contaminant level. That's been set low enough. Actually, the MCL was established in 1974. I think thereabouts when the Safe Drinking Water Act was created. It's set low enough to protect infants from methemoglobinemia. We've learned since the 1970s and 80s that there might be a possible association between chronic nitrate exposure during pregnancy and human malformations. And then we've gathered information since that MCL was established for teratogenic effects, basically cancer associations. And a lot of that data is conflicting, but there's enough evidence now that we're pretty sure that MCL is really needed. It's necessary, and some people think we might even need to lower it just because of all the toxicity and epidemiological studies that have been conducted. So I think most of you probably know that water and chemical use is increasing. We normally evaluate wastewater in terms of nutrient and metal contamination as well as pathogens. But most recently, probably in the last 20 or 30 years, we've been looking at what we call emerging contaminants. These are new, and I put new in quotes because they're not really new, but they're really low concentrations or subpart per billion levels of contaminants, such as pharmaceuticals, steroid hormones, personal care products, plasticizers, surfactants, flame retardants, and metabolites of all of those chemicals that show up in wastewater after it's been used. And these are new mainly because we have new methods and techniques for measuring them in the environment and in our water supplies. And the point of making these measurements is that we want to understand where they occur, what is the potential for exposure to human health, and control any risks to water uses, including drinking. So this article was published quite a while ago, but I really like using this when I'm talking about emerging contaminants, analyzing the ignored environmental contaminants. Really, the USGS has been a pioneer in establishing the occurrence of many of these compounds, new pesticides and degradation products. There's pharmaceuticals. We know there's a lot of pharmaceutical and antibiotics, in particular, that occur in wastewater, both municipal and livestock wastewater. There are quite a few endocrine disrupting compounds, including hormones and plasticizers that show up in wastewater and are discharged into the environment. Personal care products, even insect repellents, are one of the first groups that we found in wastewater. But this last group, the PFAS, or perfluoroalkyl and polyfluoroalkyl substances, is probably the newest group of emerging microcontaminants that have been emerging over the past 20 years or so. So I like to tell the story because I had a colleague call me, I think it was in 2014, when this episode of Gen X was detected in the Cape Fear River upstream of drinking water supply for the city of Wilmington, Delaware. And what happened was this was not a regulated chemical or substance at the time, and it was being accidentally discharged into a river upstream of an intake for the city of Wilmington. And this had happened for quite some time. I would want to say on the order of about 5 or 6 years before they became aware of the problem. And they detected Gen X in the drinking water system, in treated drinking water for the city of Wilmington. And that's really what led to the increased scrutiny of the occurrence of PFAS. Gen X is just one PFAS substance in the environment, and in particular in our drinking water systems and wastewater. They've now established that there's low per trillion level concentrations of per and polyfluoroalkyl substances. Some people call them forever chemicals in ground and surface water across the US and probably across the globe. So where did this start? I've done a little research on this, and I found that it really originated with the discovery of Teflon. Teflon is a pretty amazing product, and the story of its discovery is really just an accident. Working with gases related to refrigerants at DuPont, Roy Plunkett accidentally discovers polymerization of tetrafluoroethene, which is a gas, into PTFE in the late 1930s. After a few more experiments and tests, they decided to register this substance in 1945, and Teflon became a widely used coating as a coating on cookware, stain repellent for fabrics, and inert construction material for harsh manufacturing, industry, and laboratory environments. We use lots of Teflon in the water sciences laboratory where I work, mainly because it's inert and it's pretty durable under high temperature environments. So that's just the polymer structure of Teflon. The carbon is the light gray, and then all those fluorines. Basically, that's what the property that makes it so inert and difficult to degrade. So this is from the ITRC website. The PFAS emergence Teflon timeline, as I mentioned, started in the 30s and 40s. Manufacturing started in the 50s and 60s. I can remember in the late 1960s when my grandparents bought a Teflon coated skillet, and they thought it was the best thing in the world because you didn't need to use all this grease when you were frying eggs. It basically would allow you to fry something with very little oil or fat content. And it was in the 1970s that you might find an article or two about they detected PFOA, I believe it was, in human blood, but there really wasn't much concern about that at the time. It wasn't until the early 2000s that they started getting concerned about the occurrence of PFOA and PFOS in human tissues. They phased out those two most persistent PFAS compounds in the 2000s, and then basically is when we started developing the methods for detecting all these other PFAS substances that you'll hear about in a few minutes. So this article came about shortly after the discovery of PFOA in human plasma. They decided because of that landmark study, they really needed to spend more time measuring these substances in human tissues. But they also discovered it was really limited by the availability of purified standards. Now, that's something that we always have to deal with when we're developing new methods, is whether or not we can get standards to calibrate our instruments. And then the other problem, which we've discovered, is that we have lots of Teflon and lots of potential for contamination while we're doing the analysis in the laboratory. So that is really a difficult thing to do when you want to measure a part per trillion of something when you have a room full of something that might contaminate that extract. So we have to develop alternative extraction protocols and equipment just for doing the PFAS testing. Well, this is that landmark study that I mentioned, the first quantitative evidence for widespread occurrence of PFAS in samples of human serum by LC-MS-MS, highlighted the analytical challenges. And what they did is they spiked human serum extract, and they found, or they spiked human serum extract, and they compared the chromatograms from the LC-MS-MS to unspiked sera extract, and they consistently found very low concentrations of PFOA, which is one of the PFAS that we're measuring now in human plasma from all over the US. And they weren't intending to find that. It was another accidental discovery where there was evidence of this in places where maybe it shouldn't be. Well, if you've done any research online, there's all kinds of websites on PFAS. This is just to give you an indication of all the different classes and groups of PFAS compounds that are out there. I'm not going to go through the time needed to do all of the pronunciations of these, but just to show you how many different groups there are. The most commonly measured are those from the PFOA, which are the carboxylic acids, and the PFOS, which are the sulfonic acids. They're characterized by the structures of a carbonyl, the COOH attached to the end, or an SO3H, that's the sulfonic acid, on the end of the long fluorocarbon chain. The O stands for octate. That just means that there's eight carbon atoms in that molecule, and then in this case, the green is the fluorine atoms. Well, there's about 1,000 or maybe 2,000 different PFAS that we've measured so far, and they estimate there's on the order of 8,000 different PFAS combinations that are possible. This is just to give you a better sense of how many different PFAS there might be in the environment that we're just starting to measure. The PFOA and the PFOS are in the red, and then the C8, PFP, IA. Those are the ones that we're most commonly measuring in environmental samples. And on top of that, we have all these PFAA precursors, which are compounds that can degrade into PFAS, the perfluoroalkyl substances, and the polymers, of course, the Teflon that I started out talking about. All those can be eventually degraded into all these other compounds. So it really comes out to be quite a soup of different fluorinated compounds that we can end up with, depending on what kind of environment we're talking about. So what are the sources of these? Well, treated municipal wastewater is probably the most common source throughout the U.S. and in Nebraska. Land applied sewage sludge or biosolids. We've measured some samples of biosolids in Nebraska and easily detected PFOA and PFOS, as well as several other PFAS compounds. Industrial or municipal compost is another common source of PFAS. Some pesticides, such as the sulfuramide insecticide, can be degraded into PFAS. And then another really common source, especially in rural areas, are the AFFFs, the AAF foams that are used for firefighting. Many of these AFFFs are being phased out, but they're also still used in some areas and still in storage, ready to be disposed of. So this kind of gives you a snapshot of all the potential sources of PFAS in the environment. You know, like the laboratory, we have lots of PFAS substances used in everyday products. Of course, there's firefighting, the AFFF. There's industrial sources, consumer goods such as Gore-Tex. We have domestic sources such as wrappers for food products. All of those can wind up in our wastewater, in the biosolids, and then eventually potentially even impacting drinking water, like it did in the example from Wilmington, Delaware. Domestic wastewater likely has measurable levels of PFAS. And then when something like a biosolids is used in agriculture as a soil conditioner, that can be spreading PFAS and other emerging contaminants in the environment. And all of those can end up in groundwater and potentially impact a drinking water well. Where do they show up in our house? Well, we might find them in our electronics, guitar strings, carpeting might have traces of PFAS, wall paint and varnish, cell phones, Teflon tape used for making plumbing connections is a likely source of PFAS. And basically anything that we use today is likely going to have traces of PFAS, depending on how it was manufactured and what it's used for. So why are we concerned? The literature is still pretty new on this topic, but there's already been some literature reviews. This in particular shows a good overview of the state of the science on human health effects. There's evidence that there are developmental effects affecting an unborn baby. delayed mammary gland development, reduced response to vaccines, many issues with effects to a child, unborn child, as well as thyroid disease, increased cholesterol levels, certain types of cancer, kidney and breast cancer, testicular cancer, many potential human health effects that could be associated with exposure to human health. Now, not all of that, and probably most of that, is not through drinking water. So remember, we can get exposed through many sources, and drinking water is only one potential source for entering the human body. So that's sort of what we're trying to unravel now, or what are the primary mechanisms for exposure. Drinking water is only one, and it may not, it probably is not the most important one. So here's a little bit about the MCLs for PFAS compounds. Just last year in March, EPA proposed national primary drinking water regulations to establish legally enforceable levels called maximum contaminant levels for 6 PFAS in drinking water. Those two big ones that I mentioned, PFOA and PFOS, are really the two most important, as well as PFHXS, PFNA, PFBS, and HFPODA, commonly referred to as Gen X, as a mixture. So those last four, they decided to put those in a mixture, and they come up with a hazard index based on the concentrations that they might be measured at. EPA is also proposing health-based, non-enforceable maximum contaminant level goals for these 6 PFAS, which most of the time those goals are 0 detection. And the proposed rule would also require public water systems to monitor at least annually, and probably more frequently at first, for PFAS in their source water, notify public of the levels of these PFAS if they're detected, and reduce the levels of these PFAS in drinking water if they exceed the proposed standards. And one thing I want to point out on this slide is the incredibly low concentrations that they're proposing to enforce these MCLs at. 4 parts per trillion for PFOA and PFOS is very, very low. It's probably the lowest MCL of any compound that's been proposed under the Safe Drinking Water Act. It is a challenge to reliably measure these at these concentrations, but they're said EPA is being conservative here. They want to set them as low as they feel comfortable to protect human health. So the last few slides are just being about some of the latest research that is being done on PFAS in public and drinking water systems. Last year, a group from the U.S. Geological Survey published a survey that they had done on United States tap water, including private well and public supply wells throughout the United States. The triangles are private wells that they got samples from, and the green circles are from public water supplies. And they measured those samples during COVID, actually, for 32 PFAS. And then they assessed the detections to landscape drivers, such as source, proximity to source, proximity to industry, or municipal wastewater, as well as they looked at some temporal variability, and then they compared the levels that they measured to human health benchmarks. And what they found from that survey of around 700 water supplies across the U.S. Is that at least one PFAS was detected in almost half of the samples that they tested. They just detected them. And then the benchmarks and U.S. proposed PFAS regulations were found to be exceeded in some of those samples, both in the public and private supplies samples that they tested. And this is just a summary of the detections that they found. The triangles are the private well detections. The open triangles are the private wells that they sampled and did not detect any. And then the blue circles are where they detected PFAS in a public supply, and the open circles is where they didn't detect PFAS compounds. So you can see there's pretty random array of detections and non-detections, no real pattern that emerged here, other than that they got quite a few hits in the northeastern part of the U.S., which is not surprising, in that that's where most of industry is concentrated. So what are some of the things you can do if you're concerned about PFAS in well water? Well, National Sanitation Foundation is now working on testing the point of use and point of entry treatment systems for private wells. They developed a new protocol in 2016 to basically evaluate commercially available treatment systems. And they're currently working on some new not regulations, but guidelines for treating well water or public water systems that are contaminated with PFOA and PFOS. So in summary, domestic wells are vulnerable to contamination, mainly because of the connections that we have between our water use and the hydrologic cycle. Domestic wells in particular are vulnerable because they tend to be shallower than public water systems. And they also don't benefit by wellhead protection programs. Really, a well owner is responsible for the construction and the quality of that water, in contrast to public water systems that have to meet guidelines, pretty rigorous guidelines set down by the Safe Drinking Water Act. PFAS are a new group of highly persistent emerging contaminants characterized by highly fluorinated functional groups. They're new mainly because we've only recently had the methods and technology available to measure them in the environment. Many of these PFAS that we're measuring occur in everyday products, and there's really no escaping that. You know, a constant contact with PFAS in our consumer products are probably the biggest route of exposure. Municipal wastewater, biosolids, firefighting foams, and industrial sources are probably the most important in the environment. And then treatment technologies for removal are being tested, not yet available, but if you're concerned about your well water, I'd recommend installing a good activated carbon filter just as a precaution. So with that, I'll be happy to take any questions.
Perfect. We do have a few questions. I'll start with the first one. It's kind of got two parts to it. We have a user that says, do you know if any PTFE industrial producers are taking responsibility for the widespread exposure of PFAS by funding research into health effects or methods to decompose these compounds in the second?
Treatment, is that what you mean by decompose those compounds?
Yes, if they're funding research into the health effects or methods to decompose those compounds.
Yeah. You know, I don't know this firsthand, but I did hear that the manufacturers are, DuPont is one of the manufacturers. It's not DuPont anymore. It's, I think Dow bought DuPont. But anyway, one of the manufacturers is contributing to a fund or an effort to do more research on human health effects and ways to treat sources of PFAS. I just heard that last week, and I don't have the news source close by, but I'm sure I could find that. And should we hold manufacturers accountable? That's a good question. You know, when they first invented PTFE and all the wonderful PFAS chemicals that have been used in consumer products since the 1960s, we've learned a lot more about potential exposure to human health, exposure and effects to human health. So I don't know if in hindsight that we could hold them accountable. It's sort of like the any kind of environmental problem, we have to come up with a compromise and hope that those that are responsible for contributing to the problem will contribute to solutions for that problem. And we might have to do that through legal means, right, through the courts.
All right. Our next question says, does a reverse osmosis system remove PFAS?
RO will remove some PFAS, but not all. And that's the same is true for activated carbon. It will remove some PFAS, but not all. So I think what the National Sanitation Foundation is working on is a tandem treatment process where you have RO, possibly some ion exchange, and then activated carbon is a final filter for completely removing PFAS.
Another question we've got states, how do we get our well water tested?
There are a few commercial laboratories that are offering PFAS testing. Our laboratory does do PFAS testing. But I think many of the commercial labs are waiting until the EPA finalizes the maximum contaminant levels. So at present, it's probably going to be harder to find laboratories that offer this method. But yeah, our laboratory does PFAS analysis. We're not certified for doing drinking water, but we would certainly take a well sample and get it tested if that's what you'd like us to do.
Fantastic. I do have a question. I know that in your presentation you mentioned that water is not necessarily the main or the biggest cause. There's those household items. Is there an item or something in households that you guys have noticed is maybe more of a concern that we wouldn't maybe necessarily think about?
In a household, yeah. So Scotchgard. Has anyone ever used Scotchgard before? That was one of the first things I looked at in my house that we still have a can of Scotchgard, and it did have PFAS in it. Anything that is waterproof, that's marketed as waterproof, carpeting, fabric is going to have some traces of PFAS in it. Some of the things I've read about that I was kind of surprised to find, pizza boxes had traces of PFAS, candy wrappers, microwavable popcorn, of course, nonstick cookware. I think the old style Teflon that came out in the 60s is long gone, but there might be still some of those Teflon coated nonstick pans that are still in some people's kitchens. So those are probably the ones that I can think of right off the bat.
Very interesting. Some stuff that I wouldn't think of right off the top of my head for sure. So, well, perfect. I do think we will go ahead and launch our poll for everybody to take. If there's any more questions anybody wants to send over, maybe something here in the chat. We have a question that's, oh, the chat popped down. It says awareness for firefighters' protective gear.
So if they're using AFFF, yeah, that's a good question. I think most firefighting have switched to non-PFAS fighting foams, but we're kind of in transition so that there might be a few departments, especially volunteer fire departments, that are still trying to deal with removing these from their inventory. As far as protective gear, yeah, I don't know. I'm not aware that they recommend certain protective wear when you're using PFAS containing firefighting foams. And that's something I haven't read anything about.
All right. Well, that looks to be all of our questions for now. If there were any questions to arise later, Dr. Snow, is there a good place we could have those sent?
Yeah,
Um,
my email address.
that would be great.
Yeah. Well, you have that, so you're welcome
Yes.
to post it.
Okay. Yes, and we will send that out with some follow-ups after this presentation is posted online. So I just want to say thank you, Dr. Snow, for your time tonight. It's a very interesting presentation. Thank you to everybody for attending. And that'll conclude our event for the evening.